Thank you. So before I talk about active regression, let's first talk a little bit about just standard agnostic learning. So here you just see pairs x, y sampled from some distribution. So x is the feature vector and y is the label that you want. And here we're going to say that it's not 0, 1 labels, but it's a real valued label. And so you'd like to find the function such that y is close to f of x. And we'll stick with the simplest L2 setting for this talk. And so we're going to say that y is close on average in L2, and you want to find an approximation f hat to the true function f so that y is close to f hat, or such that f of x is close to f hat. And so in particular, let's say that just the average over your distribution of x and y of y minus f of x squared is bounded by sigma squared for some sigma that you don't necessarily know, but should be relatively small. And then the goal is to find some approximation such that our error, right, the error of our prediction, is at most relative error constant approximation. Here you could go for 1 plus epsilon. And sometimes you can get epsilon depending on exactly what you're looking for. How long do I have for this talk, by the way?
Let's say until 12:10.
Okay.
So it's a total of 40 minutes.
Sounds great. Okay. So this makes sense as a goal. Now, you could also say instead of trying to approximate y, we're just trying to that maybe y has noise. There's like the true signal f, that is what you want, and then there's noise added to it. You don't want to learn the noise; you just want to learn the actual f. And then you could, up to constant. In fact, up to constants in C, you could be saying we want f minus f hat to be less than C. And then if your noise is mean 0, you can even hope for this C to be epsilon instead of 1 plus epsilon. And so then this quantity here, which is the expected squared error, is going to appear a lot. So we're just going to call that the norm with respect to the distribution. Yes?
Just because you want to find f hat, how do you specify a function?
So it depends on, if you have some class of functions, and the algorithm is going to depend on your class. So for most of the talk, it's just going to be a linear class. So then it's relatively simple, but we're going to talk a little bit about, some sparse Fourier class, and that you can still specify pretty concisely. Okay, so this is the goal. Now the question is, how many samples does it take, and how can you efficiently compute this agnostic learning? And so let's restrict to the linear space of functions. Now, right, linear space, so this means that after you embed x with some feature vector that you know, then it's just alpha transpose times phi of x. Now, for example, polynomials are a linear space, right? They're linear functions in the embedded space. So if I have my function is supposed to be some cubic, then we're going to be observing y, which is not exactly f. It has some error that's bounded in L2. And then from y, we want to get some f hat that's close to f, or close to y. Either way, they're the same thing. And so when you think about this, it makes sense to then look at the inner product between two functions in your class, which is the expected value of f of x dot g of x. And there's the inner product that gives the norm that we were talking about in the previous slide, that norm being the expected squared difference. And when you think about this inner product, then now instead of thinking about as a function from x to r, we can think about as our observations are in like an infinite dimensional space where each dimension is what is the value at x1 at like every position x. And so the function class is some d-dimensional subspace of all possible functions from r to r. And then what we want is to project from y, the observations, to the space of functions. So you can think that under the inner product, we want to find, ideally we'd find like the best f star. But because we don't have full samples, we don't really know what y is. We have some approximation to this inner product. We're just going to get some f hat that's not quite right, because our understanding of the space isn't quite right, because we don't know all x's. We only know some subsampling of the space. And so then, right, because of that, what we're going to do is rather than going to look for the point that minimizes the expected error over the distribution, very natural thing you can try is the empirical risk minimizer, which says that once you get some number of samples, we just look at the average squared error on our samples. It will output the function that minimizes the average squared error on the things that we've seen so far. And this is a very natural thing to do. And the question is, how many samples do you need in order for this to be good enough for the empirical risk minimizer to be close to the actual risk minimizer? So as m goes to infinity, your empirical risk is going to converge to the actual risk, and then this would be the actual minimizer, which is what you want. If you take a finite number of samples, it won't quite be there, but hopefully with relatively few samples, it'll get a good job. And so we want to do this with respect to both the function and the noise, but actually for intuition, it makes sense to just think about it as saying we want to have the empirical norm approximate the actual norm over functions in our class. And there's a separate argument to talk about what happens for the noise, which I'll mostly skip. But so for now, let's just talk about approximating the norm of functions in our class. So what we want to say is, okay, if you have a class of functions, how many samples do we need for us to be able to estimate the norm of the function, just as the average squared value? And so ideally, we'll have it such that So ideally, what we'll have is that our approximation f hat is within epsilon relative to the distance to y of the true function. Because we're going to like our norm. If our norm becomes very close, then the projection under this slightly wrong inner product is going to be epsilon close to the actual projection. Okay. So let's be a bit more concrete. Let's think about a degree 5 polynomial. And our space is that x is uniformly random between -1 and 1. And so if we just sample at, say, these points, maybe we see the observation 0, 0, 0, 0, 0, 0. So if we see this, what are we going to output? Well, it's like the 0 function. Right? But it's not the 0 function, it's actually this function. And this function is pretty close because it's within some small value everywhere that we've seen. But it's not pretty close to the actual 0 function in the L2 norm that we care about, because on this small region over here is just very, very big. And so on this 1 over d squared size region, its value is like d. And so the expected squared distance can be a large constant, even though you want a small constant approximation. And so if you think about trying to prove a bound, if you were to try to prove a bound here, you would say that, well, how fast does an average converge to its expectation? It depends on the Chernoff bound. So that will then say once you take a number of samples that's proportional to the maximum value it can take, then you're going to get a very good approximation. But here the maximum value that you can take is quite large. And so the number of samples you take depends on the maximum value over all functions in your class whose norm is constant, and the maximum value of all x of f of x squared. So this is the ratio between the maximum value that f of x squared can take to the average value that f of x squared can take. And so for polynomials, this is a function whose maximum value is d, so its maximum squared value is d squared, and yet its average value is just constant. And so its k is d squared, and that gives you a sample complexity of d squared for agnostic learning of degree d polynomials. In general, you can show that with order k log d plus k over epsilon samples for any linear space of functions, you can do agnostic learning in L2. And what I mean by agnostic learning here is, well, if your noise has mean 0, then you're going to approximate the true function up to the true optimal function up to an epsilon times your error. And if you want to, if your noise does not mean 0, then you can't do that because if my noise is +1 everywhere, right? If the actual function is 0 and my noise is +1 everywhere, then it looks like it's the one function. And so you're just going to get a 1 plus epsilon approximation. Because if you have bias, then that can confuse you. But still, you can get a 1 plus epsilon approximation. But there's this k, and this k, right? So you also need the k log d, and you have this k that's necessary, and it's necessary, as you see, from the polynomials. If I don't take d squared samples, I'm not going to see anything there, and adversarial noise can make it look just like the 0 function. And so the question is, can we avoid this dependence on k, but through some other way of accessing the data? So that's what the focus of the talk is going to be. So in particular, we're going to look at other access patterns where we don't get our samples x uniformly at random, but we're able to choose them in some way. So that then we can bias, do some sort of importance sampling towards the more important parts of the space so we can decrease the sample complexity. And in particular, the goal is going to be to replace k, which is the maximum value over all x, of the maximum value over all functions of f of x squared, with kappa, which is the expected value over x of the maximum value of f of x squared. And so for polynomials, what happens is that there exist polynomials that have very high variance on the edges, but in the center, you can't be nearly as high in your variance relative to your average. And so the average value of the importance of an x is not so large, and it would just get order d. In fact, for any linear space of functions, you can show that kappa is equal to d. And then so then in the query model, which is where you can choose your x's of your choice, and then you're going to see yi drawn from the distribution for a given x. Then in this model, and then where does d come in? Where is the distribution? Well, the only point of the distribution, if you can choose x, is that this measures your norm of error. So we'll just suppose we know it because I care about learning in L2. So this is sort of the typical model for things like sparse recovery, where you can choose the points to look at. Sparse Fourier transform, you can choose the points to look at, and then you care about your average L2 error. But we're also going to look at the active learning model, which says, well, in lots of situations, you don't have full choice. You can't choose any x that you want. But you get a large collection of x's that are unlabeled. That is, that unlabeled data is a lot cheaper than labeled data, and it takes humans to label data. So you're going to give you a large collection of unlabeled data, and now you're going to choose a subset of the points to send to a human to get labels for. And you pay for that. And now you want to minimize, most importantly, the number of labeled examples you get, but less importantly, the number of unlabeled examples you get. And so you get a sample of m points x1 through xm, and we're going to choose a subset, and then we're going to see the corresponding y for that subset, and now we want to learn a function that's good on average over the distribution. And then we also, so these are for linear space of functions, and we get some results for nonlinear functions as well. Okay. So let's start with the simplest setting of just trying to get something that doesn't depend on the condition number in the query model. So a lot of the intuition comes from trying to just approximate the norm of functions in our class. And this took, as we saw, k log d samples to approximate. Particularly, it certainly takes k samples to get anything in the edge. But if we do some importance sampling, then we're going to say that we're going to sample more towards the edges. If I sample, in particular, if I sample from not the original distribution d of x, but a distribution d prime of x that scales up x by how big the value could be in the ERM calculation. Now this isn't normalized. You need to divide by the average of this. What is the average of this? Well, it's the expectation of the sup of f of x squared, which is exactly the kappa that we defined before. So now if we sample points according to this d prime, then basically just as in Moses' talk before me, now when we estimate their norm, we need to scale down again. because now we get points with probability d prime. We want to estimate the expectation of d of x, the sum of d of x times f of x. So we just have, so then in our estimate of the norm under d, we're going to have the average of d over d prime times f of x squared. And so now you can say, okay, how fast is this going to converge to the correct answer? Well, it's going to depend on, so now the Chernoff bound is going to depend on how big these values are. It's going to depend on the supremum of this. What is the supremum of this? Well, the d of x's cancel. The supremum, right, f of x is less than the supremum of f of x. And so you get exactly kappa. So it's saying that the values that we're summing and taking the average of have gone from k to kappa. And so the number of samples you're going to take for this to converge is going to go from k, which was the supremum over x of the supremum over f, to kappa, which is the expectation over x of the supremum over f. So this is going to say that we can estimate the normal functions with samples that are like kappa log d. And then, yes?
I have a question. Is it clear that this, like, couldn't there be for any x an f in your family that the supremum is the worst case?
Yes.
Okay.
There probably are. Right? For polynomials, there certainly are. But the point is that, so what made polynomials bad was that the supremum here was d, and while the average was just 1. Right? The supremum was d times the average. But if you set x to be 0, then the supremum can't be d times the average, because it's constrained on both sides. And the supremum can only be square root d times the average. And if you look at all of them on average, the squared value can be at most order d times the average. So particular for any linear space, kappa is order d, and so this would give you order d log d samples. So just to give a simple proof of that, if you just take your function in your linear space, express it in its orthonormal basis. So f of x is the sum over j of alpha j times phi j for some orthonormal functions phi j. Then the supremum over f of x squared, where f has norm 1 under a distribution. What does that mean? That means that the decomposition has alpha j's having L2 norm 1. Of then alpha dot, you can think of the vector alpha dot the phi j of x is going to be the value at f of x squared. And now, what is this? Well, the supreme, so if I take an inner product squared and the supreme over all alpha of L2 norm 1, it's going to be maximized if alpha is in the direction of this vector. So you're going to set alpha to be phi j divided by its norm. And so the value you get is exactly the sum of phi j of x squared. And now the expectation of this is going to be exactly d. So for linear spaces, this expected sup is exactly d. And so this gives the order d log d bound. Okay. So far what this says is that if we sample our points x, so that we like upsample proportional to the supremum of f of x squared, then we get an order d log d sample complexity. And this is essentially the same as leverage square sampling, right? And so really what I think is, right, so in terms of estimating the norm, this is basically what you would get from leverage square sampling. The other aspect of it is showing that the noise behaves well. Because you don't have, if you're familiar with leverage square sampling, you don't have any, we're not looking at the noise, and so this doesn't guarantee that the noise is good, but because your leverage square sampling is well spread out, you can show it's bounded in expectation. You can also think of leverage square sampling as analogous to Spielmann-Srivastava graph sparsification. And so then the question is, well, that's an n log n graph sparsification. Can we use linear samples graph sparsification? And so you can't with independent sampling. You can show again by coupon collector that if your x1 and x2 up to xd are all drawn from the same distribution, then you would need d log d samples. But if you do it with non-independent sampling, then in fact you can avoid this. So this is analogous to BSS, which is the linear sample graph sparsification, but BSS doesn't work for this setting because
It's deterministic.
exactly, it's deterministic. And if you're deterministic, then that means you choose your points x as like a fixed set. So if I want to learn a degree d polynomials, I'm going to look at x1 equals 0.5 and x2 equals 0.7 and so on. But then my noise is just bounded on average. And so it could be adversarial and placed entirely on those positions. And so you can't get any guarantee. So you need a randomized version of BSS, and that's in fact known. So Lee Sun gave a randomized method for sparsification, and we show that that suffices for this problem. That the randomization is enough to make your error be bounded in expectation. Okay. So just the guarantee that you get again is that for mean zero noise, our error is epsilon times the noise you have, and for generic noise, your error is 1 plus epsilon. Okay. So this is for the query model, but as I was saying, in a lot of situations, you can't choose the x's as you want, and you don't know what the distribution on x's is. Instead, you have a collection of unlabeled data, and you want to choose which ones to get labels for. So this is now the active learning setting. So again, we have unlabeled data, we want to choose a subset to get labels for. And there's two goals now, right? So we want to minimize both the number of unlabeled points we need and the number of labeled points we need. So then you can ask, okay, suppose you only cared about minimizing one of those in isolation. So if we only cared about minimizing the number of labeled points, what is that? Well, we're going to choose infinitely many unlabeled points because there's no cost to it. What happens if we do that? Well, now we learn the distribution because we get infinitely many samples from the distribution, and we can query any point we want in the support of the distribution because we have all the points. So this is precisely the query model. And so it's precisely the query model. That means that we know that theta of d samples is necessary and sufficient for, at least for linear spaces. Okay, so now suppose we only cared about minimizing m and not s. So then what would we do? Well, we just label everything because there's no cost to choosing everything to label. If we're labeling everything, then we're in the agnostic setting because we don't really have any choice. We're just getting a bunch of labeled points x, y. And so in the agnostic setting, that means we need k log d plus k over epsilon. And so then our result is that, in fact, both of those you can get at the same time. That there's not a trade-off between these two parameters. This many unlabeled points is enough to learn enough about your distribution to do a theta of d labeled points. In this talk, I'll mostly cover the leverage score sampling based order d log d version, but then I'll give a little intuition for how the order d sample algorithm works. And there has been prior work. So there was a result of Sabato and Munoz that got d log d to the 5/4 bound. And then there was some concurrent work very recently that got an order d log d bound using not leverage score sampling, but volume sampling. And that's another algorithm actually that may well get an order d bound, but we don't know how to prove it. Okay. So any questions on our goal?
Did the Wormuth paper just get an unbiased estimate? Did it actually get they actually get the same error guarantees that you have?
Okay, so I think they don't actually look at the difference between, they don't really look at going from error on x1 through xm to error on the distribution. Right, so we're saying that we're gonna generalize as well as not just do well on the empirical distribution. I don't think they do that, but that's actually not really the hard part of the result. Yeah. Basically, because of matrix turnoff, if you do generalize on x1 through xm, then you're gonna generalize on the rest of the distribution. Basically. Yeah. Okay. So let's start with the warm-up. Right? So there's two distinctions between the active learning setting and the query setting. Right? There's that we don't know the distribution D, we need to learn it from our samples, and we can't query any point we want, we can only query the points that we've seen so far. So let's start with just getting halfway there by saying, suppose we know the distribution, but we can't choose any point we want, we can only choose the points that we've sampled, we have the unlabeled samples for. So in this setting, we can now simulate the query algorithm where we wanted to sample proportional to this D prime by rejection sampling. So that means that whenever we wanted to sample points proportional to D of x times the sup over f of x squared. And so we'll just choose to label any point that we get with probability proportional to this. Okay, with proportional to this, that means the probability has to be less than 1. So the scaling factor is going to be dividing by the maximum value this could take. The maximum value this could take is exactly k. So we're going to label each point x psi with probability equal to 1 over k times this sup. And so now, when we do this, the number of labeled samples we're going to need is just d log d, because we're now getting our labeled examples exactly from the distribution we wanted for the query algorithm. Then the question is, how many unlabeled examples do we need in order for this to work, in order to get the number of labeled examples we need? Well, the chance that so if you think about any example coming in, what is the probability that a random example coming in is going to be labeled? Is the expectation over x of the probability that you're labeled? Well, that's the expected sup divided by the k, which is cap over k. And so this says that in order to get, which is d over k, so in order to get the d log d samples that we need to have labeled, we just need k log d samples unlabeled. And so that means that the k log d unlabeled samples and d log d labeled samples are exactly what we need to get the active learning guarantee in this simpler warm-up where we know the distribution. That's great. Now suppose we don't know the distribution. Well, where does this algorithm use the distribution? Because once we sampled it, we just are doing some ERM. So once you get your samples, it doesn't actually use the distribution. The only place where you use the distribution is to decide the probability of sampling. And where do you use the distribution to decide the probability is that the distribution appears right here. That we look at all functions in our class and we take f of x squared divided by the expected value of f of x squared under x from our distribution. That means all we need from the distribution is to be able to estimate the norms of functions in our class. And so, so we need to estimate norms of functions in our class, but that is exactly what Matrix Chernoff said you could do with k log d samples. So we just need to learn these things, need to estimate the norms of functions, k log d samples suffice. So this means we can do it in k log d samples and d log d labeled examples. So now I'll briefly describe how to improve this from d log d down to just order d samples. And so the d log d comes from coupon collector. So if you just think like, if my distribution on x is, if the domain is 1 through d, so x is either 1 or 2 or 3 up to d, then I need to choose at least one of each of those points. If I choose independently from some distribution, I'm going to miss some point. So I need to now have a dependent distribution in order to do order d samples. And so in particular, what we're going to say is we're going to start out sampling from this distribution that we liked for the first point. But now once we have an x, we no longer need to get points that are the same. Is we're going to bias our future examples away from the points that we've seen so far. So we're going to choose the ith example from a distribution di that depends on all the points we've seen so far. But it doesn't depend on the examples we've seen so far. So we can still do this for active learning because we know which rows we've selected. And then we're going to need two properties for our collection of di in order for this to work. So the first probability is that we need to be able to preserve the norms. Right? So we're going to need to do something like the matrix Chernoff that took k log d, that took d log d samples from leveraged score sampling. But then we also need to have our noise being bounded, because we need to say something about how the BSS linear sample sparsification doesn't work, because it's deterministic. Right? Our samples need to be random enough that the noise doesn't concentrate and mess us up. And so the first property of having the norms preserved is saying that, well, right, so naively you just say that your average value of d over di f of x squared is close to the actual expectation. And the noise variance being bounded turns out, okay, it's a little bit of calculation, is saying that each individual distribution di has a bounded condition number. And as long as each one is bounded condition number, then that's going to say that the variance due to the noise is small. And you can show that the expectation due to the noise is 0. Now this we don't actually know how to prove. You can only prove it where you replace the 1 over s by some alpha I that depend on the distributions. But you can do that. It's a little bit nasty. Anyway. So you can do this with least sparsification if you analyze, look carefully at how they do this. So that basically, right, they were focused on the norm preservation, but you can show that the distributions that they pick also give you the noise variance bound that you need. Okay. So this is all so far, yes?
Is there something about like rounds of adaptivity, or you do need each query to be adaptive?
So you're adaptive to the x's that you've chosen, but you don't look at the y's at all. And so you're still doing it for active learning, right? I mean, it's like, eventually you're just getting some joint distribution over your x's, and you're not looking at anything. It's just a way of computing a joint distribution. Yeah. Now I think it is like, yeah, I think it's an interesting question whether you could like give an explicit statement for the distribution. Like for polynomials, you can say we're going to pick one sample from the outside 1 over d squared, another sample from the next 2 over d squared, and so on, and that works. And we don't know how to do that in general. But yeah, so this is adaptive, but it's not to anything that you learn, and so it still suffices. Okay. So for the last bit of my talk, I'll discuss an extension to nonlinear spaces. So rather than what happens if you're not a linear function, but for example, a sparse Fourier transform. So here, now our function class is that f of x is the sum over our d points of vj times e to the 2 pi I fjx, where fj is the frequency, vj is the value. And we're going to have no assumptions on our vjs. And our fjs are going to, and almost no assumptions on our fjs, right? So we're going to allow them to be very, very close to each other. And they're going to be bounded in some range. And again, we're going to say you can sample points. Suppose you can sample them uniformly in some interval. You can sample them however you want in some interval. We're going to measure our error as just L2 norm over this interval. So you can think of this as people playing music, relatively few frequencies going on, and we're listening for a finite period of time. And we can choose what points in this time that we're going to sample and see the value that we're getting. And so again, we're going to need to be able, if we want to do this well, we're going to need to be able to estimate the norm of this function. And if we're going to estimate the norm of this function, then that's going to depend, as we saw from the beginning of the talk, on the sup divided by the expected value. The sup of the sup divided by the expected value. And you can show that if you set your fj's if you set them all to be converging to 0, then by a Taylor expansion, you can actually express any polynomial as a limiting value of this class. So the set of sparse Fourier representations is larger than the set of degree d polynomials. And so in particular, we know that it's got to be at least d squared, right? At least d squared is k. But we need to analyze what they are. So again, right, uniform sampling is going to depend on the soup. We don't know what this soup is for sparse Fourier transforms with continuous frequencies. But so we, along with Zhao Song and Daniel Kane, we're able to show that it's at most d to the 4th times some log factors. And we know that it's at least d squared by this relation to polynomials. And so this then gives you sample complexity bound. But we can do the leverage score sampling style importance sampling where we pick a point proportional to its we pick a point proportional to the sup over f of x squared. And then our estimate of the norm is going to sample proportional to kappa. And we can show that kappa for sparse Fourier transforms is basically d. So we've gone down from this somewhere between d squared and d to the 4th, we're not sure, to somewhere between d and d log squared d, as the number of samples required to estimate a single function well. And so this, if you're familiar with it, this is analogous to the distinction between the Markov brothers. So for polynomials, there's the Markov brothers inequality, which bounds the maximum value a polynomial can take in terms of its average by d squared. And there's the Bernstein inequality, which bounds the value, the expected value. Yeah?
This is inequality developed by Markov's brother, or it's by Markov, who calls it brother inequality?
I switched the apostrophe. It should be brothers apostrophe. Yeah, so there are two Markovs that jointly did this inequality in the late 19th century. Right. It's actually kind of funny, right? Because in concentration inequalities, we also have a Markov's inequality and a Bernstein's inequality. These are not those. These are different inequalities that are still very related to each other. Yeah. Okay. So just as a sketch of this proof, we take the degree d polynomial, p of z, whose roots are at e to the 2 pi I fj delta. This polynomial is going to depend on fj, and it's going to depend on this delta. It doesn't depend on exactly what x you're looking at for f of x. And then if you look at any position x, and you evaluate this expression, the sum over all I of beta I f of x plus delta I. So this is just a linear combination of an arithmetic sequence of positions of looking at this function. Then this, if you expand your definition of f and you transpose, switch the order of summation, you can show that this is a linear combination of the evaluations of p, which is equal to 0. So just to illustrate what's going on, we're saying we have our function f that has a sparse Fourier transform. We look at a sequence of d positions that are each separated by delta. And we're saying that there exists a linear combination, the sum of beta I times this value plus the beta 1 times this plus beta 2 times this, and so on, such that the sum is equal to 0 here, and it's equal to 0 here, and it's equal to 0 here. That it's equal to 0 regardless of what position, what offset x you have. And what that means then is, in particular, if you look at the largest coefficient you have, it says that the value that f takes at x plus I star delta is certainly at most the sum of the values it takes at the other positions, because the sum of all of them is equal to 0. And what that would mean is that the value that f takes at any position x is bounded by the sum of the values it takes at in an arithmetic sequence moving outside it. And if you do a little bit more care, you can change this from an absolute value. You can find, basically, if you do a bit more care, you can find a set of d of these, or d different linear combinations that are orthogonal to each other, or mostly orthogonal to each other. And so you can replace this L1 bound with an L2 bound, up to some constants. So you can say that the value that f of x squared is bounded by the sum of the f of x squareds in an arithmetic sequence around the value, around this position. And that then means that if you then just integrate delta from 0 to 1 over d, or to like 1 minus x over d, you can say that the value that f of x takes at any position x is bounded by its average value times d divided by 1 minus the distance. So this says that if x is not very, very near the edges, then f of x squared can't be too big. And so then you get a bound on the expected value that f of x squared can take. And this then gives you a bound on the sample complexity required to learn sparse Fourier transforms in the continuous setting. Okay. So then the point is, what we've shown is active learning can be optimal in both the criteria of k log d plus k over epsilon unlabeled examples and order d over epsilon labeled examples. And we can also get some improvement for Fourier sparse settings. Now, what I showed you was basically tight, at least up to these log factors. We don't have the analogous bound to matrix turnoff, and so there's a dependence on the net size that's not optimal. I think some interesting questions for future work are, one, going beyond L2 and linear spaces. So for example, can we do logistic regression? And another is for, when people actually do active learning, they'll often sample points and then do multiple rounds. So after you look at some points, decide where to sample next. And in this worst case agnostic setting, that's not useful. And I think it's a good question whether it is useful for worst case bounds in something like logistic regression, or what you should be doing for other settings. Anyway, thank you.
Questions for Eric?
So about nonlinear spaces, couldn't you, approximate a nonlinear function, a bounded nonlinear function by polynomials, and then?
But how many polynomials is it going to take? Right. So if it yeah. So for example, for sparse Fourier, you have this. If you have high frequencies, then they're spinning around very fast, and it would take a very high degree polynomial. It wouldn't be bounded in terms of d.
Would it help you if I gave you boundary conditions? Because it looks like that's hurting you in your analysis.
What sort of boundary conditions are you thinking?
So if you're sampling from 0 to 1, I give you f of 0 and f of 1. I mean, you can argue that the expert knows those extreme values, right?
Yeah. I mean, so if you just told me f of 0 and f of 1, then you can still make, I think, with no noise. That's an interesting question, right? So if you're allowed to have noise, so in our model, I can't just query f of 0 and f of 1 because I would have noise, and so I can't trust the points that I would get. Yeah, maybe you can get better results if you're sure, if you're confident in their values. I don't know. Thank you.